we do the sampling of the original analog signal at a certain sampling frequency. For this example, it was 8,000 kilohertz, sorry, 8 kilohertz, which is 8,000 hertz, that is 125 microsecond per between every observation. So we do this observation at every 125 microsecond intervals, and we got these numbers of individual voltage values at those timestamps, at those time incidents. And then we converted all of these things into binary numbers, 4-bit numbers. 4-bit in this case means that all of our individual number will be made up from 4 individual binary digit. So whether the total value of the digit is less than 4 or more, we have to have this. Now, there are some interesting information that I'd like to talk to you. One of the things is that if we have a 4-bit system, then how many total individual variations of number can we accommodate within that? So the way binary system works is that if we have a binary number, let me just show you a sort of an example for how this works. Let's say if we have a binary number that reads 10011001, let's say we have a binary number like this. The way the physical, there are many different ways to go for it. The way that we can easily convert this is this thing is going to be multiplied by 2 to the power 0. This thing is going to be multiplied by 2 to the power 1. This thing is going to be multiplied by 2 to the power 2. This is going to be multiplied by 2 to the power 3, 2 to the power 4, 2 to the power 5, and 2 to the power 6. So this is a 6-bit number that I've written over here because they are all the digits, and then you have to add all of these. You just add all of these things with the multiplication. So here you can see that if you multiply 1 with 2 to the power 0, you will end up with 1. 0 multiplied by 2 to the power 1 doesn't give you anything, so I'm going to write 0 over here. 1 multiplied by 2 to the power 2 gives you 4. 1 multiplied by 2 to the power 3 gives you 8. 0 multiplied by 2 to the power 4 still gives you 0. Then 0 multiplied by 2 to the power 5 still gives you 0. And then 1 multiplied by 2 to the power 6 gives you 2 to the power 6 is how much? 34? No. 2 to the power 6 মানে কত হয়?
64.
64?
Yes, sir.
Thank you. Thank you. So, yeah. So, I'm going to get 64 right over here. So, if we just add up all of these numbers, so each of these numbers that we're getting over here is basically the binary digit multiplied by their relevant 2 to the power something. What is important that for the first digit we got 2 to the power 0, which means for the 6th digit we got 2 to the power 5. This is a very important thing. It's not 1, 2, 3, 4, 5, 6. It is 0, 1, 2, 3, 4, 5. That's the way it works. That's very important because this observation will be very instrumental for the next part of the discussion. So if we just add all of this, you get the total decimal number that is equivalent to this binary expression. So one of the important part that you have to understand that if you have a 4-bit number means you're going to have altogether 4 places in it. The biggest number that you can express using a 4-bit expression is 1111. The biggest number that you can express with a 4-bit expression is 1111. So what is the total value of this thing? The total value of this thing, of this number, happens to be 1 plus 2 plus 4 plus 8, which gives you 15, not 16. Some of you might feel like, for those of you who are not acquainted with computer sciences or binary number studies, this is the first time that you are coming across. You might feel like that having a 4-bit number means there should be 2 to the power 4, which means this gives us 16 options. So the maximum number to be expressed by this thing should be 16. That is not true. The maximum value that you can accommodate with this number is 15. Then what is the relevance of the 2 to the power 4 thing? I mean, why am I even bringing this up? To confuse you? No. Here is the deal. Whenever you are expressing a number in 4 bits, the total number of numbers that you can express by a 4-bit number is still 16, because the smallest number that you could express by a 4-bit number system is 0, 0, 0, and 0. So how many altogether individually different numbers or individually different integer numbers that you could possibly represent using a 4-bit number? If you start from coming from 0, you have 0, U1, 2, 3, it goes all the way up to 15. So altogether, how many different numbers are here? You have 16 numbers. That's the sense of 4-bit number system, that if you have a 4-bit number system, you can express 16 different individual values. 0 is definitely one of those. So the maximum possible value for that 4-bit number system is 15. Similarly, if you have a 5-bit system, the total number of options for number to express decimal numbers to express 2 to the power 5, which would be 32. So you can express a total of 32 different numbers, which means 0 being one of the included numbers. The maximum number that you can express in a 5-bit number system is 31, which means I can tell you that 11111, if you have 5 ones written in this fashion, the total value of this number in this is in binary, and if you write this decimal value, this will be 31, not 32. So important bit, if you have a 4-bit system, you can express a total of 16 numbers. Because 0 is also one of those numbers, the maximum value of the 4-bit system number expressed can be 15, not 16. That's the important bit that I want to tell you. আচ্ছা, এরপরে যে জিনিসটা আমাদের জন্য ইম্পর্টেন্ট, সেটা হচ্ছে যে how does this whole conversion system works? কোথায় গেল এই যে how does this whole conversion system work? There are multiple steps to it, and I'll talk to you about these stuffs periodically, and also we'll also see some sample questions from the worksheet as well for better understanding. But let's go for this whole discussion. This whole page basically discusses what happens over here, which I discussed over a bit for the last class, and starting from today's class. So let's go for these paragraphs and try to make sense of what these things have. So I'm going to read so you can tag along. The theoretical candidate should be able to understand that the digital transmission of speech or music involves analog to digital conversion, ADC, this is a short form, on transmission, and digital to analog conversion on reception. So on the transmission end, it has to be converted from analog to digital so that the signal can travel to the transmission channel in a digital form. And then on the reception end, that digital signal should be once again reconverted back to the analog form so that it can be played as we can achieve the original format. Then it says, candidate should be able to show an understanding of the effect of the sampling rate and the number of bits in each sample on the reproduction of an input signal. So এই জিনিসটা কি, সেই জিনিসটা এখানে আমরা আলাপ করতেছি, খেয়াল করো। The electrical signals derived from speech to or music are analog audio frequency signals. The voltage generated varies continuously. To convert an analog signal into a digital signal involves taking samples of the analog waveform, that is measuring its instantaneous voltage at regular. This is actually a meaning of the word sampling. It means measuring its instantaneous voltage at specific timestamps at regular intervals of time. The instantaneous or sample voltage is converted into a binary number that represents its value. So in that case, we convert those individual decimal measurement that we get, we convert them into binary equivalents. For example, the instantaneous value of the analog signal is 66 volt. The binary number could be 0110. For an instantaneous value of 13 volt, the binary number could be 1101. Note that a binary digit is referred to as a bit. One binary digit is referred to as bit. The most significant bit, MSB, the bit representing the largest decimal number, is written first. The bit representing the lowest decimal number, 1, is known as the least significant bit, LSB, and is written last. Acha. Let me reference to you that what this actually means. I'll take a little bit of time to explain this part. If you have a 4-bit system, you have 4 places to write your bit numbers. The first one is called the MSB, and the last one is called the LSB. Most significant bit, least significant bit. Now you might wonder, why do we even bother for this? I mean, what's the significance of this? There is a certain significance of this preference of bit system, specifically whenever we consider the communication channel that we have to use to make the data transmission possible. So before let me give you a bit of an idea. The idea of most significant bit is that if you somehow mess up this bit, for example, let's say, or in the original signal this bit is to be 1, if somehow in the receiving end this bit becomes 0, you're going to have a radical change of this whole data. Least significant bit on the other hand means that if you had a 0 over here and let's say then it becomes 1, or if it was 1 then it becomes 0, there are only two options over here. So if it just flips to the other value, other binary value, you're going to have a slight change, the slightest amount of change on the output data system. So that's what we're going to, so most significant bit and the least significant bit. So the significance or the importance of the bit goes down as we observe from left to right. What is really important for all of you to understand that in sense of accuracy of information, all the bits are important. But in sense of priority, the left one is more important because that can change more fraction of the data or more part of the data in its value. Why it is important? I mean, why this discussion is even required? I mean, what are we doing here practically? What is happening? One of the whenever we're going to see different paths for the communication systems, which comes a bit later, there are multiple different systems that we're going to see. We can have a wire pair communication system. This is the very old telegraph system where we had Morse code sent through dots and dashes, like that. And from that thing, people could reconvert the signal. It's the very first communication. So this is a wire pair communication. Then we have the coaxial cable. The coaxial cable is still used, largely used in today's world. We in Bangladesh, in Dhaka, mostly see them for the dish antenna cables. They come in this is the copper wire, then there's a white plastic sheet, and there is a metal mesh around it, and there comes a black coating of the wire. This is basically the dish antenna cable. For that purpose, we see it more often. And then we have the radio link, and there is no picture for the radio link because it's just a microwave communication, you don't see it. But there is a way for the process for how it is used. Whenever we have radio wave or microwave link, I mean, whenever we are using electromagnetic waves, we always prefer to use a parabolic mirror like this, and we place the transmitter or the receiver at the focal point of the parabola so that we can convert them all to become parallel lines, or we can receive them as parallel lines, which somewhat makes the attenuation through the passage of through the medium of communication medium channel somewhat smaller. So that's a very important thing. The other very important part is that one advantage transmission using optical fiber advantage এখানে দেওয়া আছে। আচ্ছা, আমি যে পার্টটা নিয়ে কথা বলতে যাচ্ছি যে কেন এমএসবি এবং এলএসবি ইম্পর্টেন্ট, সেটা হচ্ছে there is a certain way by which we can send the information, যেটা আমরা আচ্ছা এটা আমি আলাপ করি, যেটা হচ্ছে okay, I need to pull out the worksheet. By the way, তোমাদের এই কমিউনিকেশন চ্যাপ্টার ওয়ার্কশিটে এই টেলিকমিউনিকেশন রিলেটেড যা কোশ্চেন দেখবা সেগুলো সব বাদ। I was lazy enough not to physically discard them, so they are still included in your worksheet, but you can all skip them. These used to be a part of your syllabus, but not anymore. But you still have this part. এই জিনিসটা এখনো আছে। So let me talk about this block diagram. Here in this block diagram, you essentially can see how does the part of the syllabus that is still within your within the different bundles of the syllabus. Inside this part, we used to have the PSTN network, Public Service Telephone Network, PSTN, which is not a part of the syllabus anymore. So we can forget about this. So this is a microphone signal. We are talking to the microphone, music, voice, whatever. We have an amplifier. Then we have the ADC. ADC means it converts the analog into digital. That is basically this conversion. That basically means this conversion from decimal to binary. So you're basically converting it ADC. So from analog, you're converting it into digital. ADC means analog to digital conversion. Then there is a bus which is converting it into parallel to serial converter. Parallel to serial converter is a certain device. This is just a rectangle label as the device, but there is a certain electronic device which is responsible to convert all of these individually produced bit numbers into a continuous series of bit numbers. So what it's going to do Let me just take a snapshot of this one, maybe. So one thing that I really need to understand that whenever we are doing the sampling, we are doing the observation of the original analog signal every 125 microseconds. So we are making observation at 0 microsecond, 195 microsecond, 250 microsecond, 625 microsecond. It goes on like that. We're making those observations at these microseconds. Now we are going to convert all of these individual values into their decimal equivalent, into the binary equivalents, into their binary equivalents. Well, what is really important that whenever we'll convert these numbers, 8 will be convert into 1000 directly out. So out of this 8 decimal value, you get 1000, the 4-bit number, decimal number, sorry, the 4-bit binary number immediately. From 12, you get 1100. From 14, you get 1110. So after every 125 microsecond, you have 4 bits available for you. These 4 bits are not being produced over the duration of this 125 microsecond. This is very important for you to understand. These 4-bit numbers are produced at every 125 microsecond interval, not over the duration of 125 microseconds. So you have 8 or exactly at 0 microseconds. So you have 1000 over here, not over this gap. Over this gap, you have nothing. You are basically waiting for new data. At this 125 microsecond, you once again have 12 volt, which you are receiving exactly at 12 at this 125 microsecond mark, and then you have these 4 digits, 4 bits on your hand. So there is 1100, and then you don't have any more data for the next 125 microsecond. That's how it's produced. So the information that we generate in the process of sampling, they are produced instantaneously. That's the important bit, not over a duration. So these are the data. This is the type of data which are produced in 4 bits. So this 4-bit is one number, this 4-bit is another number. This is what we call a parallel data. To be able to send this number to this stream of data into a communication channel, that communication channel can be a wire pair, can be a coaxial cable, can be a radio communication, can be a optical fiber, whatever your communication channel that is convenient, preferable, cheap, and affordable for you to use. To be able to send this digital data into the communication channel, we have to convert them into one single stream of data. We preferably cannot send them as parallel data as is. So that parallel to serial converter, what it essentially does, it takes all of this data. Oops. So what this device does, it simply copies those data, takes those data, and simply merge them all into one single continuous stream. So like this, and then like this, and this, and this, and this. So are you getting my point? The parallel to serial converter basically merges all of the individual parallel data into one single stream of data, which is this shape of the data is what we call a serial data. This serial data is then fed into the communication channel, which goes to the communication channel. So if it's a wire-based system, it goes out as high voltage and low voltages. If it is an optical fiber system, it goes out as bright or dark. For how much duration do you have dark for for a step size of 125 microsecond, and then for how long it was illuminated? That's what we measure. For example, if you have an observation over here, I mean, the way an optical fiber would work is really interesting. That here you can see 1. It means if the optical fiber is sending out this 1, it will inside the optical fiber in the source is going to be illuminated for 125 microsecond, and then it's going to shut off. It's going to shut off for 3 into 125 microseconds. So it's not going to give out any light for 3 times that, which means 3 times this would be 425. No, 375. 375. Sorry, my bad. 375. So for 375 microseconds, the light source would be completely off. This 375 microsecond should not be read as 1. On the receiving end, it will read off this 375 microsecond darkness as 3 zeros, because it would know that it is supposed to read every 125 microsecond as one single piece of bit. Then it has two ones, which means it's going to be turned on for 250 microsecond. It's on. Then it has two zeros. Then it has three zeros. Then it has 1 0, and then it has two ones, two zeros, one, and then it has a lot of zeros right over here. How many? 1, 2, 3, 4, 5. So it's going to be switched off for that many 5 into 125 microsecond. That's how the signal will be sent through the channel. This process of converting the whole parallel set of data into one stream of data is what we call the serial conversion. So there is an electronic device which does this job, and that's when we send the data through this device. Let me finish this discussion, and then I'm going to come back to the MSB and LSB. I'm going to come back to this part after a while. So what we do, we send this thing through the parallel to serial converter, it goes to the communication channel, and then it's going to get received on the receiving end through an antenna or an aerial. Now the first thing that after to start the processing process, what the device have to do, on the receiving end, it would know because we would instruct the process by the digital system, it would know that this set of data that we're sending that has 8 kilohertz sampling, and it should also know that it is a 4-bit data system, which means on the receiving end, it should have a proper knowledge that every 125 microsecond is to be considered as a single bit, and every 4-bit makes one decimal number. So what essentially means that it's going to observe the light sources or the voltage durations within for multiples of 125 microsecond and convert them into bits, and then it's going to chop this entire stream of data into group of 4. Group of 4 means what? Something like this. It's going to chop this data into group of 4. Like, so let's say this is my first decimal data, and then this is my second decimal data. Then maybe this is my third decimal data. So it's going to chop this whole series of number into 4 apiece, because it would know from our instruction that it is the system of 4-bit data transfer. So every data will be divided into chopping of 4. After chopping, each of these data would be converted as individual different numbers. So this will become 8, this will become 12, this will become 14, blah, 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 blah. So you will basically recover the whole digital signal into its original decimal values. This process of chopping the whole series number system into individual 4-bit groups is called serial to parallel converter. So that's what this electronic device, which is labeled as a rectangle with a label box, does. So here the parallel numbers are converted into series to make them feasible, to make them possible to be sent over a single communication channel as ones and zeros, and then on the receiving end, that serial data is chopped into parallel numbers, and then all of these individual numbers will be then converted into DAC, that's digital to analog conversion. And after doing this DAC, basically what we get is this graph. After doing the DAC, this is this thing, the recovered analog signal. So digital to analog, that's DAC, digital to analog conversion. ADC stands for analog to digital conversion, and DAC stands for digital to analog conversion. So DAC does the recovery of the analog signal, and after recreating the whole signal by assigning all these values one after another, we get this zigzag shape. And that's how we do the communication transfer process possible. So this is something that is important for us to understand the purpose of this whole thing. Any questions so far? এই পার্টটা বুঝা গেছে কিনা?
Yes, sir.
All right. The next piece of information that I would like you to understand is that there is before we human beings could develop this electronic component, parallel to serial converter or serial to parallel converter, before we could develop this one, there was a way for faster communication channel, or maybe it is still in use today. If we want to, every bit of data transfer that you do inputs some lag in your data transfer process. Every type of conversion that you're going to do will take some time. It's not instantaneous, like it's not 0 second. It might be small, but there will be some time. So the fewer number of steps that you can do within this flowchart diagram, the faster your communication will be, the less latency you're going to have, the less lag you're going to have in your communication channel. So one of the ways that to avoid this lag or to avoid these two boxes, parallel to serial converter, serial to parallel converter, is to use multiple channel for each individual bit. That might sound a bit crazy, but I'm going to show you an example of this one. I think it is available over in our booklet. I hope I can find this. Let's have a look. It's also available. Continuous. Yep. This one, multi-channel cable. Go yellow. Yes, have a look. This is one of the systems where it totally gets rid of the serial to parallel converter or parallel to serial converter. Here is our signal, send it to the ADC. Then we have a multi-channel cable. This is the important bit. So how many channels do you see over here? If you give a count, 1, 2, 3, 4, 5, 6, 7. So there are 7 channels over here. It can be used for a 7-bit data system, or less than 7 if you want to keep one of the channel as your, what can I say, as your reserve line. The idea of this thing is that through these channels we're going to send all of the bits of a single byte. In this case, if this is a 4-bit system, this whole thing is usually called a byte. I think I'm correct. Computer আছে কারো? Anyone have computer as a subject?
Yes, sir.
These 4 bits together is called a byte, right? Am I correct?
Sir, 4 bits can nibble bola hai. 8 bits is called a byte.
4 bits ki bole?
Sir, nibble.
Okay, that's a new word for me. Okay, thank you. So this 4 bits as a group is called nibble, and 8 bits is called a byte. So okay, so these 4 bits, other than sending these 4 bits by making it to convert undergo a parallel to serial converter and serial to parallel converter, what we can do, we can send all of these 4 bits simultaneously through a 4 channel if we have that. For example, in this case, we have in this figure, we have 7 channels over here. If you choose to use, if you want to send, let's say, a 7-bit system, you can send 7 individual bits, which means light or dark or high voltage or low voltages, ones or zeros, through these 7 channels simultaneously. So you're going to send 1 byte or 1 nibble out of this ADC directly, and they will all simultaneously pass to this channel and be received over here. And this simultaneous reception of all of this bit will comprise one single data. So in this process, by having this multi-channel cable, you can essentially skip the requirement of the serial to parallel converter, parallel to serial converter. This is also another way of communication, which can increase a bit faster data if you want to achieve that. This is more commonly, this type of communication is more commonly used for LAN games, where the lag is very, very small. Do you guys know what LAN games are? Anyway, forget about it. Now, why is this? Why am I talking about this thing with such high importance? Because this is in this process of this multi-channel cable is where this MSB and LSBs are really important. These two things become really important. I mean, this is just one of the factors, not essentially the whole thing. This is one of the factors that if you have, let's say over here we are sending a 7-bit data. 7-bit data is actually never used. It's all either 4-bit data or 8-bit data or 16-bit data. It goes on like that in a multiple of 2. But let's say, because we have 7 channels over here, let's assume that we have a 7-bit data system over here. You would not, at any cost, want to mess up the MSB. If you somehow mess up the MSB, your entire value of that data would be messed up. If zeros become ones or ones become 0, you will be altogether messing up the whole thing. So you'll be losing pretty much the whole integrity of your communication system. Whereas having lost the LSB will bring in some variation. For example, your Ours could be ours, or there may be slight changes which might be acceptable but not recommended, but acceptable. So the preference of a huge channel is that if you are trying to send a 7-bit channel over here, and let's say in the process of your communication somehow one of the channel becomes dysfunctional or one of the channel becomes jammed, you can cut off the LSB and use the first 6 bits for your thing, which means that you are never going to mess up your MSBs. So the preference of those bits basically comes along this line, that you're always going to try to send the first bits, and you're going to, if you have to, you can get rid of the last bits. This is mostly required for whenever you have multi-channel cable system like this. That's one thing. But this is the physical significance for the MSB and LSB as far as I have come across to study and read. But if you are doing this whole thing of serial and parallel conversion in a stream like this, all MSBs and LSBs, the whole thing is important, because it is really important exactly where you are chopping these numbers. For example, if you just think about it, if this chopping location gets shifted by only one space, you'll be having a whole mess of data. I mean, if all of these rectangular boxes shifted one digit to the right, then you would not be getting the original data. You'll be getting a whole lot of non-similar data that you did not send. So that's the significance of this whole thing. Any questions so far? বুঝা যাচ্ছে কিনা? Hello? সরি, বাসা থেকে করা ছিল। এই পর্যন্ত বুঝে গেছে কিনা? কারো কোনো কোশ্চেন? I can see some chat window. আচ্ছা, yes sir, বুঝে গেছে। আচ্ছা, so the next part is actually more simple. কই গেল PDF? এই যে PDF। সেটা হচ্ছে I'm going to go back to the paragraph to where we shifted from MSB and LSB. Okay, here comes this paragraph. So we are now at this paragraph right over here. A digital signal consists of a series of high and low voltages. A digital signal consists of a series of high and low voltages. A 1 represents a high voltage and a 0 represents a low voltage. A 4-bit system used in the example, a 4-bit system is used in the examples in this booklet. In reality, 8 or more bits would be used for any sampling. So 4-bit sampling is actually not used. It is good for make explanations, make discussions, because it's simpler to transfer. But in reality, we prefer to have more bits. Why do you prefer to have more bits? I'm going to come into that after a while. Then it says in the next paragraph, figure 3.8a shows an analog signal frequency 1 kilohertz. The signal is sampled every 125 microsecond. A sample frequency of 8 kilohertz. The sample voltage is shown in figure 3.8b. It will be noted that the value given to the sample voltage is always the value of the nearest increment below the actual sample voltage. This is really important. এই সেন্টেন্সটা তোমাদের বুকলেটে সবাই মার্কার দিয়ে মার্ক করো, অথবা হচ্ছে হাইলাইট করো, অথবা হচ্ছে রেড পেন দিয়ে মার্ক করো. This is a very important sentence. I'll explain what this means. It should be noted that the sample given to the sample, it is to note that the value given to the sample voltage is always the value of the nearest increment below the actual sample voltage. আচ্ছা, এটা আচ্ছা এটা অ্যাপ্লিকেশন দেখাই এখন সমস্যা নাই I have time so I can actually find out a graph where these conversions are done so that I can explain what this sentence mean বাকিটা যারা শুনতেছো তোমরা কি বুঝতেছো if you have any question please raise your hand or just ask the question right away I appreciate this what I'm trying to show you is I need to find out a graph where this conversion has to be done okay okay so let's have a look at this graph this is a certain analog signal so this is millivolt versus millisecond so this is the original analog signal we are trying to convert this for sampling frequency of for sampling frequency where the output is measured every 0.25 millisecond so at 0 second you have 6 so you convert 6 into 4-bit system that gives you 0110 you write this up then the question is asking us to fill up this remaining of the boxes so at 0.25 you get exactly 10 so you convert 10 into binary you write this over here at 0.50 you get 14 you write that over here at 0.75 however you get 15 you can see that this is pretty much exactly between 14 and 15 so you convert 15 and you get at that value and then at 0.75 and then at 1.00 you get this value now have a look at this one this is the important bit this number over here is not at 11 neither at 10 this is somewhere between 11 and 10 11 would be at the halfway mark of these 5 boxes so somewhere over here is 11 right over here and here we have 10 now the question is between this 10 and 11 which one should be our designated sampled voltage value do we go for 11 or do we go for 10 this is exactly where this sentence come into play have a read it should be noted that the value given to the sample voltage is always the value to the nearest increment below the actual sample voltage so in this case the actual sample value voltage was between 11 and 10 what is the voltage what is the designated voltage below that level 10 volts so the actual sample voltage for this 1.00 millisecond position this is gonna be what should it be 10 or 11 what do you think
স্যার 10 হওয়া উচিত
it is supposed to be 10 but I see too few responses বাকি কি আসলে ক্লাস করতেছো নাকি তো you are just here and you are just goofing off okay apparently my confusion gave us some 10 values okay I'll move on so this is the important bit so if the actual sample voltage is somewhere between two of the designated numbers that we are working because here the values that will be working for our syllabus all these numbers are going to be integers so you're not going to be working with decimal values if you want a decimal values I'm not very sure about this I think decimal values can be used but to be honest we can have the variation planned in a way that decimals can be avoided. In your syllabus, you don't have to deal with decimals. So I didn't learn whether there are decimals or not. You have to deal with, but I can tell you for sure that you don't ever have to deal with decimal values for your syllabus. So you'll be always dealing with integer numbers. So if it is below 10 and 11, you have to go for 10. So that's the significance of this word which I wanted to discuss. And then comes the remaining part. In this particular example, an analog signal of 40.3 volt would be sampled as 14 volt and one of 3.8 volt would be sampled as 3 volt. So it's not mathematical rounding, it's always the below one. The resulting digital signal is shown in figure 3.8c. Each number is a group of 4 bits and these groups are separated in time by 125 microsecond, which we talked about. The choice of sampling frequency is important. Here comes a very interesting paragraph. The choice of sampling frequency is important. A lower sampling frequency means that less information can be gathered from the analog signal. More than 80 years ago, it was shown by Nyquist that in order to be able to recover the analog signal from its digital conversion, the sampling has to occur at a frequency greater than twice the highest frequency component in the original signal. Now, Nyquist showed that. I'll explain what this means. Have a look. In order to be able to recover the analog signal from its digital conversion. So if you want to get meaningful, I mean, you can convert any signal, any analog signal into digital signal with any sampling frequency for that matters. I mean, no one is stopping you to do that conversion. But the digital signal that you're creating out of a given analog signal, once you recover the original analog signal, I mean, you get this grainy graph. How does this graph is at all mean useful in comparison with this graph? I mean, does this graph somehow, I mean, fulfills the requirement for us to have this one? That's the important bit over here, that in order to recover, in order to be able to recover the analog signal from its digital conversion, the sampling has to occur at a frequency greater than twice the highest frequency component of the original signal, which means if your original audio signal is composed with a lot of different frequencies, which is a very common thing for music. You can have a lot of instruments going by, you can have opera voices and other instruments, many of them can have a very high frequency. Whatever the highest frequency in that audio input analog signal is, the sampling should occur at a frequency more than double of that. The sampling should occur at a frequency more than double of that. This was shown by Nyquist. You don't have to know why this is important, but I'm going to give you a little bit of example for why this is important. Try to have a look. Let's say here is an object that is moving left and right in this manner. This is an oscillation scenario. Let's say the time period of this oscillation is 1 second, which means after every 1 second, this object reappears on the same position. Now, let's say if you want to observe the motion of this object by sending pulses of light, which means high frequency, this is basically sampling. If you send pulses of light from a source or strobe light means flickering light, but you control the frequency of this light. If you send strobe lights into this setup of a time period of 1 second, then what you are going to see, if for the first scenario you find the object over here, for this after exiting 1 second, if you send the light, you're going to see the object in the exact same position. After exiting 1 second, you're going to find the object in the exact same position. So even if the object is moving, even though the object is moving, if the object's time period is 1 second and you send light waves every 1 second, you're basically going to get the reflection from the exact same position of the object. The object is actually moving, but the object is reflecting the light while being at the same position. So your observation would be, you would be deciding that the object is stationary, but the object is practically not stationary. Problem 1. What if the time period of this object was half second? Think about it. Having the time period half second means it takes no, not half second, sorry, भूल गई से. भूल गई से. What if the object has a time period of 1 second and we send the pulses as at 0.5 second? If our send pulses are a bit more faster, so we are sending the pulses of light every 0.5 seconds. Before I go for the 0.5 second, I would like to confirm that এটা 1 সেকেন্ড হলে যে অবজেক্টটা সবসময় একই পজিশনে দেখা যাবে, এই জিনিসটা সবাই বুঝতেছো? The object is moving, but it is always reflecting light being at the same position. এই আইডিয়াটা কি বুঝা যাচ্ছে? Everyone, can you please respond with a quick yes or no?
জি স্যার।
Okay, people who are not responding, apparently I can find them out. I didn't see a response from Tashfia, Samiha, Nushin. Mursalin. Masharab. Okay, Anya responded. Thank you. Afrida Islam. Afrida Islam. Yes. Okay. I think we have most of them here. So now if we start sending the light pulses with a interval of 0.5 seconds, try to understand this. So this was a hertz of 1 hertz, one pulse per second. This is 0.5 second, which means this is 2 hertz. So now we are sending the pulse at double the frequency of the object's original vibration frequency. So this was moving at 1 hertz. Now we are sending at exactly 2 hertz. So if we send the light pulses at exactly 2 hertz, what's going to happen? Try to understand. Let's say when the first light pulse shows up, the object was here going in this direction. If the object has a total time period of 1 second, it means it will complete half the motion in, it will complete the full motion in 1 second. So after exactly half second, it will cover half the motion. Try to understand. If the object was here, so let me just draw it. So this is the full motion, going all the way back and coming up over here. This whole thing is going to take exactly 1 second. So in about half second, the object would be appearing somewhere else. Let's say the object might be, it might show up over here. So the object might show up over here, covering half the distance of this thing. So the object will be showing up over here for the, at 0 second, you're going to see the object over here. After half the second, the object is going to go up all the way up to its terminal position, and eventually when it's coming back, we'll be seeing the object over here. And then after another half second, we'll once again see the object as the object comes all the way up over here and eventually comes back over here. That's why we're going to see the third of reflection. And then we're going to see the fourth reflection over here. Then we're going to see the fifth reflection over here, and it goes on like that, which means we're going to continuously see the object appearing at these two locations. We're not going to see continuous movement. We're going to only see the object popping up in 2 locations. So we might as well think that this object is moving back and forth in this manner, where the amplitude of the motion is only this much, because we are seeing the object moving back and forth between these 2 positions. But the actual amplitude of the object was actually far more bigger. So this does not give us a full information for how much the object is moving. That's the problem. We can see the object in 2 different positions, but we cannot see the full motion. If we send the frequency, if we send the light pulses at a frequency higher than 2 hertz, let's say if we send it at, let's say, 2.1 hertz, for example, that small variation will cause the object's observation to slide off every once in a while, a little bit, by a little bit. As a result, you will not be seeing the object at the terminal positions for every single one of your observations, but every once in a while, you will see the object coming to the most terminal position. You will be able to get the reflection of these positions every once in a while. And that will enable you to have a proper judgment of the full path of the object. Do you understand this part? This small variation will basically do what? It will make your observations move a little bit for every consecutive observation. So you're going to see the object in one position. The second observation is going to be not exactly over at this position, but it's going to be somewhat earlier, because now your frequency is a bit higher, so your time will be a bit lower. So it's going to be a bit earlier, and so on and so forth. So you'll be seeing the object in a lot of positions, but if you combine all of this data together, you can find out a total trajectory of the whole thing. Even if the object is moving in a curved manner, you can get that curve. If the object is going around in circles, you can get that whole circle. You can get the total motion of the object by compiling all of the observations. That is possible only if the observed frequency is more than double of the object's original frequency. Does this physical explanation make sense?
Yes, sir.
I hope it does. If it doesn't, you can ask me questions right now, or if you feel like you can ask me a question later, no big deal. So that's the important bit, that to have the whole, so that's what Nike showed, that in order to be able to recover the analog signal from its digital conversion, which means that you have done the digital conversion, but as you recover, are you going to get the full exhibit behavior of the original analog signal out of the digital conversion. To have that, our sampling frequency needs to be more than double of the highest frequency component of the original analog signal. Twice the highest frequency component of the original analog signal. এটা না হলে আমাদের recovered analog signalটা original analog signalকে properly resemble করবে না, will be having a significant loss of data. So as a result, in the telephone system, the highest frequency is restricted to 3.4 kilohertz. The highest frequency is restricted to 3.4 kilohertz because the sampling frequency is 8 kilohertz. So whenever we use basic telephone, I'm talking about landline, the sampling frequency for landlines is 8 kilohertz only. So being 8 kilohertz mean that you can work with the highest sampling frequency of up to maximum 4 kilohertz. So they don't directly use 4 kilohertz. They have used that the highest frequency is restricted to only 3.4 kilohertz. So 3.4 kilohertz means that double of this would be 6.8 kilohertz. So they have kept a bit of gap of 0.6 kilohertz to the double value, but that makes sense. I mean, if you keep the sampling frequency of 8 kilohertz, the maximum allowed audio frequency could be up to 4 kilohertz, but they have preferred to keep it up at 3.4 kilohertz. I don't know why do they have to take this 0.6 kilohertz gap. I honestly don't know this, but this is very much valuable within the acceptance line. Achha, Mugdha, you asked a question. I'll pick this question after a while. I've seen it. আচ্ছা, এরপর যে কোশ্চেনটা আছে সেটা হচ্ছে এবার পাটা খেয়াল করো, in the manufacturing of the compact discs মানে হচ্ছে basic series, the highest frequency is 20 kilohertz. That is the human audible range is 20 kilohertz, because we want to cover the whole range of the audible range to give more quality to the sound creation. And the sampling frequency is 44.1 kilohertz. So this is the sampling frequency for most audio files. After the analog signal has been converted to a 4-bit digital signal by the analog to digital converter, the digital signal is transmitted. The original signal can be recreated by passing the 4-bit numbers into a digital to analog converter. This is illustrated in figure 3.8D, where the original analog signal of figure 3.8A has been recreated. So this is basically the recreation of the original signal. The output of DAC is grainy and is not smooth. This is the important part, where I'm going to talk a little bit as well. The output of the DAC is grainy and is not smooth because the numbers of bits limits the number of possible voltages. Number of bits limit the number of possible voltage levels. With 4 bits there are 2 to the power 4, 16 levels. With 8 bits there are 256 levels, and so on and so forth. As described above, a higher sampling frequency also enables more detail of the analog signal to be recovered. আচ্ছা, এই দুটো লাইন আমি একটু তোমাদেরকে ডিটেইলসে বুঝাই, খেয়াল করো। I'd like to pick up this image. Okay. Okay. 120, 115. Should that work? Works. Beautiful. So print screen is a good idea. Print screen. Okay, we need this much. Okay, let me try to explain what I'm trying to explain. Try to have a look. One of the important things for us to have a more similar signal, recovered signal, like the original analog signal, is essentially to make these gaps smaller. I mean, let me give you a bit of an example. For example, wouldn't this signal look more like this one if we had smaller gaps with smaller step size and smaller curves like that. I mean, I cannot draw a perfect up and right curve, but if we had graphs like this, so what I'm going to show you is that if we, here's the deal. In this case, we made the observation after every 125 microsecond. What if other than making 125 microsecond of thing, I mean, this was happening for an 8 kilohertz sampling frequency. What if we had 16 kilohertz sampling frequency? Or maybe 20 kilohertz sampling frequency. So if our sampling frequency was much bigger, then the observation time periods would be more, there will be more incidence of observation within this part, which means other than producing 8 and 12 volt within a gap of 125 microsecond, you'd be getting another set of data over here, maybe another set of data over here. So you'd be getting two, let's assume that if we have two more data over here, so that would be 3 times the frequency. Let's say it's, now we're talking about 24 kilohertz. So if it's 24 kilohertz, between these two things, you're going to have two more data. So that's that. If you have two more data's done, if you have two more data in between this whole gap, that would give us two more staging point in between to this line, which means, let me rub this off. If we had two more points, let's say one over here and another one over here, this graph, and this was the original curve, this graph would look like this. From 8 to this point, then a small rise, then up to this point, then a small rise, then up to this point, then a small rise up to this point. So this small number of steps gives you a more varied option, which looks like more like this of a straight line as like this one, rather than a single big step like this. So if we had a much higher sampling frequency, we could observe the original analog signal more often, and that would keep bigger fraction of the data of the original analog signal, and that would be better, that would have been better to create a more similar signal of the original analog signal. That's basically means that higher number of sampling frequency would make the simpler, make the recovered analog signal less grainy and more look like the original analog signal. This is only because of sampling frequency, but there is a catch. Catchটা হচ্ছে, if you increase the sampling frequency, you would simply producing the double, the more data. For example, for 8 kilohertz, you are producing 8,000 instances of data every second. For 24 kilohertz of sampling frequency, you are producing 24,000 instances of data every second, which means if you keep everything same, simply increasing the sampling frequency from 8 kilohertz to 24 kilohertz will make your file size triple. Simple. If a song sampled at 8 kilohertz was 10 megabyte, if it is sampled at 24 kilohertz, it will simply become 30 megabyte, the same song. This would be a bit less pleasing to ear. This will definitely be a more pleasing to ear, but your file size is gonna get bigger. So there is a question of optimal use, or there is a question of preference, that what is more important for us. Do we want to have a smaller file size, or do we want to have a much more data? That is basically what matters. So if you have access to high-speed internet, you might actually want a bigger file data because it doesn't take that much time for the download. But if you're using, let's say, GPRS 2.0 in some part of the world where the internet connection is really poor, then only having the information or just having a workable music or workable voice or workable news might be good enough for you. In that case, you might as well require a small size data. So all variations are required depending upon how much you can afford and what position are you in. এই আইডিয়াটা বিষয় আছে স্যাম্পলিং ফ্রিকোয়েন্সি এর আইডিয়াটা যে if we have bigger sampling frequency, there will be more data and that would make it more look like the original signal. I hope it does. If it doesn't, then you can ask me a question. Raise your hand and you can then go ahead. Question I have to pore আসছে. One more thing that this observation that I talked about for the sampling frequency, the sampling frequency. This essentially covers what change we can bring about for the x-axis, for the horizontal axis, so that we can take more data. What we can do for the vertical axis? Is there a way that we can get more refined situation for the vertical axis? The answer is yes. For this represented data conversion system, we went for a 4-bit data combination system. We went for a 4-bit data combination system. Now, what is important that for a 4-bit data combination system, the maximum number of levels that we can accommodate is 16. So you can see that it starts from 0, it finishes at 15, because 16 set of data means 0 through 15. It does not mean 0 to 16, because that will be 70 levels of data. So although they have labeled 16 over here, but the maximum this graph could go up is up to 15, which means এই যে অ্যানালগ সিগন্যালটা আমরা নিয়ে কাজ করতেছি, this analog signal that we're working, the op amp from which this analog signal was amplified, that op amp should have a supply of plus minus 15 volt, so that the output should not become more than 15 volt, if I can put it that way. So because you can maximum cover up to 15 volts. If you use, let's say, 5-bit data, then we can have 2 to the power 5, which is 32 set of levels, which means in that case we can have 0 through 31 volts. So in that case, the number of divisions on this axis would be even smaller, just half. Now you have, for the same information, if the same information over here is represented in 15 divisions for 16 levels, but if you had 5-bit data, this same information could be vertically divided into 32 levels with from 0 through 31 numbers. That brings about a much smaller size. This basically means that other than what can I say? Other than, how can I put this? Other than cutting a large piece of cake in chunks of like soap pieces, you are cutting them off like in toffee pieces or chocolate pieces, like that. So if you are looking at the data in a much smaller variation, so in that case, that would essentially do what? That will increase the number of step size in our vertical scale. So it means that if you had, let's say, if we had, let me use green over here because I've already used the other two colors. If we had more variations over here, green. If we had more variations over here, it would mean that these data might as well be, other than having it read at perfectly 12, we might have read it at 13. We might have read for the in-between, which means this would really give us the opportunity to acquire more precise information out of the analog to digital conversion. But once again, that poses another problem. The problem is that for a 4-bit system, every 125 microsecond you are producing 4 bits. If you have a 5-bit system, you'll be producing 5 bits. That's an increment of 20% of data, from 4-bit to 5 bits. If you simply go from 4-bit to 8-bit, for example, it means that for every sample instances, you'll be producing 8 bits over here. So that will be 8 individual bits producing 1 byte. So it means the higher bit system that you're going to work for, you're simply going to make more data. That data would help you to produce a more beautiful graph for the recovered analog signal, but the volume of that file will once again become bigger. So that this also comes in the similar idea that if you want to use a higher bit system, your file size is going to be bigger. If you want to go for a lower bit system, your file size is going to be smaller. Similarly, if your sampling frequency is higher, you're going to have a large file size. Your sampling is smaller, you're going to have a lower file size. The way MP3 music works is exactly this. I mean, if you for those who have bought music CDs ever, you know that in a CD essentially has 768 megabytes of data. That's the capacity. I think I'm not wrong. One audio CD holds about 750 megabyte. Let's say about 750 megabyte. Let's say you have 10, 11 songs in it, which means about 7.5 megabytes each song. Whenever you convert it to MP3, it can come down into 2.3 or 4.3 megabytes. So what essentially do we do whenever we convert an original song into an MP3 music? We basically reduce the sampling frequency, or in some cases, we also reduce the bit number. Now, our ear can only distinguish that much. If you are not trained precisely to hear the difference of sampling frequency and bit number variation, you would not be able to tell the difference. I mean, a high bit number sound and a low bit number sound might as well feel to be same for you, because we human beings, over the years of our evolution, if that's the true thing, we have become more dependent on our visual and become less dependent on our auditory senses. So a slight increase in pixels information is very easily captured by our senses. I mean, we can very easily distinguish between 360p and 480p. We can, although that's a very minor variation. But a difference of, let's say, 24 kilohertz sampling frequency and 12 kilohertz sampling frequency might not be detected by most of the people. That's what I'm trying to mean. But if you're in the audio business, a high quality data, having a high quality data essentially can have you more data. And this also brings us to another interesting information, which might be a part of your discussion in your question, is that can we make a small file size into larger file size just by incrementing the data? For example, let's say if a certain audio file, it was 8-bit and let's say 100 kilohertz of sampling frequency, without having the original analog signal, can you simply make it 16-bit and 200 kilohertz? The answer is yes, you can, but that would not increase the quality of the whole thing. That will simply make the file size bigger. I mean, you'll be basically looking at the same thing twice. So, if you want to have informative large file, you need to have access to the original file. This is why when digital recordings are done, the initial recordings usually can rake up to like a really high amount of data. For example, let's say up to one single song can rake up to 40-50 gigabytes, because they capture every single pass of sound at a very high bit rate and a very high sampling frequency. But that is not essentially required for us regular people, because you would not essentially want to have one song that is 40 gigabyte in your cell phone device or in your PC. That simply is not worthy unless you are in that business. So that was my point. Questions? Anyone? No. Okay. So I entertain one question that Mugdha asked us in the chat window. Anyone can have a look at that. Mugdha asked us that why can't we observe the object at the terminal position? Mugdha, did you ask this question for the scenario where we were doing for 1 hertz or 2 hertz or 2.1 hertz or half hertz? Which one?
Sir, 2.1 hertz.
If we go for 2.1 hertz, this gives us a bit smaller time than 0.5 second, right? Because a bit high frequency, it means a bit smaller than this one. So let's say this is 0.49. I'm just guessing guessing this now. Let's say this observation duration is 0.49 second, which means you are going to be able to see the object at a varied position than earlier every once in a while. You're not going to be see the object right at the edge. You might be lucky and find the object right at the edge on your first go. That's the probability. But if you think for regular scenarios, on your first observation, the object is most likely not to be on the terminal position. But if you keep on observing the position with sending lights at this hertz, there would come a certain position, where your object would be, the light will be reflected off when the object is located at the terminal position. So if you observe the object, for example, let's say 5-6 minutes, and if you compile all the data, you'll be getting the entire pathway. It's not that we would not be seeing the object at the terminal position. We would be seeing the object at the terminal position, but not continuously, because like I said, that we are sending strobe lights, we are sending pulses of lights. We're not seeing the object continuously like we regularly see in our regular life. I'm saying that we are sending the light pulses at 2.1 hertz, which means we are sending 2.1 light pulses every second. So the instant the light is falling, that's when we are seeing. So we are basically seeing 2.1 times the object every second. So are we seeing the object moving continuously? No, we're seeing the object stationary at a fixed position when the light is falling on this. What I want you to understand is that the duration of the pulse is very small. That does not give you an understanding whether the object is moving or not. The duration of the pulse is extremely small, like instantaneous. For example, like over here, if you look at the graph, that whenever we observed evaluated the instantaneous signal, we did not evaluate it over a duration of, let's say, 0.1 microsecond. We measured it instantaneously. That what is the signal? 12 volt, period. So 12 volt comes in. That kind of a light pulse that I talked about. Does it make sense?
Yes, sir. And sir, if we use 2 hertz, we can observe it at the terminal position, right?
Not essentially. If you use exactly 2 hertz, then you'll be seeing 2 alternate positions continuously. So let's
As in the
say,
same ones.
yeah, we'll be seeing at those 2 positions continuously and alternately.
Okay,
Because
sir.
it would take exactly 1 second to go back and forth. So that's why sending a sequence of 2 hertz. I mean, let's say you're sending with this specific message, you're sending 2 pulses per second. So if in one pulse you see it here, in the second pulse you see it here, in the third pulse you see it here, in the fourth pulse you see it here, in the fifth pulse you see it here, in the sixth pulse you see it here. So you will keep on seeing the object at 2 positions, and that's basically it. And these 2 positions doesn't even have to be on. It has to be equal distance from the position. You might as well see for one point, you might as well see the object over here, and in another case, you might also see the object right very close to the equilibrium right over here, and you will see only these 2 positions. That can also happen.
Okay, sir. Got it, sir. Thank you.
Sure. Any further question? No. So, I hope these paragraphs made sense to you. For most of it, I tried to be elaborate as much as I can. And then the next part that we have is a bit tardy. Tardy means elaborate, no? What does tardy mean? Delaying or delayed beyond that, this is also late. Sorry, not tardy, my bad. The next part is actually a bit elaborate, it's theoretical. Here we have the advantage and disadvantage of different type of communication channel that we can have access to in our regular process. Here we have wire pairs, and then we have coaxial cable. The benefit of coaxial cable is that these outside metal mesh, copper braid, outer conductor, it's actually a mesh of copper. It doesn't necessarily have to be copper. Copper is very good. I mean, having copper is very good because copper is a good conductor. Other than having copper, we can also have what is this thing called? We can have other metals, for example, aluminum or other metals that can make a good mesh. That's also possible. And the thing is that this metal mesh is actually connected to the ground. And benefit of this thing is that if there is some electromagnetic wave that is coming across this pipe or this wire, this electromagnetic wave will produce some voltage into this wire, and that voltage will immediately become grounded because this metal braid is connected to the ground. As a result, this inside wire would not be affected by this external electromagnetic wave. So whatever the signal that is sent through this wire would remain mostly unaffected. So this is basically like a safeguard. I mean, this copper braid or this mesh is basically a safeguard for the data that travels through this inside wire. This is basically our main communication channel, which is the inner conductor, and this is basically to the mesh is there to get rid of the reduce the amount of attenuation or noise pickup it might do from the surrounding. So we're getting minimizing that factor. And then we have radio link. You can read through these parts. If you have any question, you can ask me later on. That's up to you. And I just talked a little bit about the shape of this thing. And then we have this part. এই পার্টটা নিয়ে আলাপ করা লাগবে। So এই জিনিসটাও অনেক সময় পরীক্ষা আসে। What are the advantages of optical fibers? Optical fibers have a lot of advantages. There are a couple of information that we might want to talk about. Key term actually. এইখানে একটা key term আছে, যে crosstalk. I want you kids to underline this thing in your booklet. Have a read of this one. Wire pairs provided very simply. In monocombination, wire pairs are used mainly for very short distances or with low frequencies. A very common example for wire pair combination is the intercom of a building. That's wire pair. If high frequency signals are transmitted along a pair of wires over an appreciable distance, long distance that is, repeated amplification must be provided at regular intervals. This is due to the very high attenuation of the signal. Energy is lost as heat in the resistance of the wires and also as radiation, since the wires act as aerials. A further problem is that the wires easily pick up external interference that degrades the original signal. If several wire pairs are arranged next to one another, they will pick up each other's signals. This effect is known as crosstalk or cross-linking and gives very poor security, as it is very easy to tap a telephone conversation. The bandwidth of a pair of wires is only about 500 kilohertz. Consequently, as a means of carrying a large amount of information, it is extremely limited. So wire pair is only it's a very cheap option for very small distance communication, where you are not going to be using it for a very large amount of data transfer. That's what the wire pair can be used. Like I said, for the intercom of a building. I mean, even if all the people are talking at the same time, you cannot produce a lot of data on this channel. So for an internal communication of an intercom, a wire pair combination works. The couple of things that I would like to tell you is that cross-linking or crosstalk is the type of communication whenever you have unwanted, that's the important term, whenever you have unwanted connection across two communication channels which are placed side by side, or you can say that the information that is passing through one of the data channel somehow entered the other data channel unexpectedly. That's what we call crosstalk. And this basically is obviously is unwanted, and communication channels which are prone to do cross-talking or cross-linking, they give a very poor security. Poor security means that data security is one of the key things in today's world. I mean, if you think about amenities for today's world, as long as we human species are alive, I mean, data is currently considered as one of the most important resources, because in a consumer-driven world, data is very, very, very valuable, like really valuable. Please, have you seen the serial Silicon Valley? Anyone? TV series Silicon Valley? No one? Okay, for those who haven't, I highly recommend this. For those who have, you know why I'm recommending it. Anyway, so yeah, if you haven't, you might as well take a look at it. It's a nice one. It gets a bit slow at the somewhere in the middle, but it's overall enjoyable. I'd say. In terms of security, it is important that communication channels should be secure. Secure means a communication channel should not be such that it can be tapped from the outside. Tapped means that you set up a certain mechanism by which you can pick up the information that is traveling through the communication channel and extract that information without letting any of the user on either end of the communication channel knowing it. Basically tapping telephone wires, for example, what the CIA or the FBI people used to do back when wired telephones were there. So that's what they meant, tapping the telephone. So in those cases, they would simply produce some electromagnets, very sensitive electromagnet across the exposed telephone wire somewhere in the communication channel. And whenever they would have a call, they could replicate that exact information and could be able to hear it without the other people know. So Wi-Fi has a very poor security in that manner. Coaxial cable has some security in that fashion, because the reason we say some frequency is because typical coaxial cable, if installed when installed properly, would not pick up external disturbances, because that's the purpose of the braid. But if someone wants to tap into the channel, what they have to do, they have to cut open the plastic covering, remove the copper braid, remove the polyurethane insulator, and then place a sensitive solenoid across the copper wire, through which they can generate the electrical signal convert into voltage and EMF. The part that is open, the copper wire part that is basically open, that should in that case pick up some external noises. Now, people who are using this using coaxial cable for the communication process, if they are smart enough and careful enough, should be able to detect that additional disturbance suddenly coming up in their channel. Now, if they are not careful, they would not know. But if they are careful, they should be able to detect that, which means that this gives us some security sense, some security, because you cannot altogether, I mean, the people, the users have a probability, or they have some sort of capability to be able to detect that tapping procedure, but not 100%. So we say this is some security, but not definitely not 100% security. The only communication channel by its own virtue that gives us 100% security is the optical fiber communication channels. This is because optical fiber communication channels work in the process that light is always undergoing total internal reflection within the inner boundary of the optical channel. If you cut open the optical channel at any point, you're gonna be letting that light out. So, and the moment you let that light out of that optical fiber channel, light would not be passing on to the later part of the communication channel. So, so there are two parties which are communicating, and the third party wants to interfere in between. So, if the third party interferes an optical fiber communication somewhere in the middle, typically the second party would not be receiving the first party's information. So the communication is hampered, so they would know there is a problem, they would come to see and repair it and take care of it. So that's why we say that is very high, and there is no way to get the information out of an optical fiber channel by placing a sensor outside an optical fiber channel, because all the light is always kept within. This is a very important part. That's how an optical fiber works, total internal reflection. So all the light information is actually kept within the optical fiber, so it's not coming out. So there is no logical way that you can place a receiver on the outside and expect to receive a significant amount of reading out of this thing. It simply doesn't work that way. So let's look at these points over here, which actually sometimes shows up in our exam for questions. The advantage of transmission using optical fibers indicated below. Optical fibers have a wide bandwidth. This gives rise to a large transmission capacity. Signal power losses in optical fiber are relatively small. This allows for longer uninterrupted distances between regenerated amplifiers and reduces costs of installation. This is important, that because the energy is not dissipated out, so most of your energy is kept within, so you do not have so much attenuation. Attenuation basically means the weakening of the same signal over distance. Yeah, I'm fine. I was just stressing out my lungs to finish my long sentences. I'm good. So that's that. And then the third point is the cost of the optical fiber is much less than that of the metal wire. Yeah. Well, there is one thing that you really have to understand. The cost of a single optic fiber is definitely cheaper than that of a metal wire currently, because optical fibers are largely in use. But when optical fibers were initially developed and they are not widespread like today, optical fibers used to be very, very, very costly. The reason optical fibers today are cheaper than metal wires, because optical fibers are now produced in large quantity, and as a result the manufacturing cost has gone down, so everybody can afford this. The diameter and weight of optical fiber cables is much less than that of metal cables. This implies easier handling and storage. Well, one thing, this actually makes sense. Optical fibers have very high security since they do not radiate energy, and thus there is negligible crosstalk between fibers. So you can actually clump up a good number of optical fibers side by side and use all of them individually to transfer data communication simultaneously, and there is almost no possibility for them to have crosstalk, because the lights you're going to be sending through each of the optical fiber channel are going to be transferring through the channel individually. So this increases the bandwidth or the amount of data transfer that is possible per second simultaneously. This allows the optical fiber communication a very high bandwidth. And to be honest, optical fibers do not pick up electromagnetic interference. This means they can be used in electromagnetic noisy environments, for example, along electric railway lines. In fact, optic fibers cables are installed along the route of the national grid. Optic fiber is ideal for digital transmission since the light is obtained from lasers that can be switched on and off very rapidly. Okay. আচ্ছা, এখানে আমাদের একটা দরকারি জিনিস যেটা জানা লাগবে, এই জিনিসটা আমি বলবো, তোমাদেরকে আরেক সেট ম্যাথ দেখাবো, ম্যাথ দেখা আজকে ক্লাস শেষ। এখানে একটা দরকারি জিনিস হচ্ছে, আচ্ছা, বিফোর আই গো ফর দিস আই জাস্ট রিমেম্বার ওয়ান ওয়ার্ড, মাল্টিপ্লেক্সিং কথাটার মানে আমি বারবার ভুলে যাই। Does anyone know what multiplexing mean? Multiplexing, confused in two parts. Does it mean multiple different data channels within a single optical fiber, or does it mean multiple different radio stations operating in a single geographic location? এই দুটার মধ্যে যে কোনো একটা, বাট আমি এটা ভুলে যাই। First one. Yeah. In telecommunications, several telephone calls may be carried using one wire. Yes. So optical fibers, in the other hand, actually has the advantage to make multiplexing. Multiplexing means being able to have multiple different communication through the optical fiber channel simultaneously. So the way this can be achieved, there are multiple different ways this can be achieved. For example, let's say you have one optical fiber channel, and actually a single optical fiber is very small and very thin. Why is not there any banana for scale? Anyway, optical fibers are actually very, very small. For example, this is also, I was looking for a scale with something on the I'm not finding what I'm looking for. Anyway, the point that I'm trying to make is that one of the key advantage for optical fibers is that we can do multiplexing. Multiplexing means you can do simultaneous communication of multiple different users within a single optical fiber communication channel. What that essentially means, the way it can be achieved is that, let's say, one set of communication is done at 100 frequency of light, 100 hertz frequency, for example. You can do another communication at 120 frequency, 20 hertz. Or you can do another communication at, let's say, 300 hertz. To be honest, you can make 100 hertz communication back and forth if you set those two lights at 90 degrees with each other, which means if you set those lights to become to be polarized. So 100 hertz communication going back and forth within a single optical fiber channel, and you can have multiple of these communications within the same optical fiber channel if you have different frequencies. This allows multiple communications to be simultaneously happening within a single optical fiber core. That is essentially what multiplexing is. This is highly unachievable within a metallic wire, because within a metallic wire, you can only send high voltage, low voltage, high voltage, low voltage. You cannot send a different set of high voltage and low voltages through a wire, because there is only one way to measure high voltages and low voltages. So it is quite impossible to have multiplexing in metal wire scenarios, but in optical fibers, it is very much logical to achieve it. This is why to make large amount of data transfer, we do not practically need a lot of optical fiber. But whatever the optical fiber that there is, it requires a lot of protection. You can see over here that optical fibers do have a huge amount of protection on them. This is the actual optical fiber. This is the wire, water resistance jelly casing, 2.3 millimeter. Then we have a set of steel wires around those things. Then we have a copper tubing around this thing. Then we have a high density polyurethane insulation around this whole thing. And that whole thing basically makes the submarine cable through which the whole world is connected. So this entire thing is there for the protection of these four different optical fibers, and these four optical fibers are doing good enough job to replace, let's say, thousands of square foot of cross section of copper cable, something like that.
So sir, এভাবে ইন্টারফারেন্স হওয়ার একটা চান্স থাকে না?
Within the optical fiber,
জি স্যার।
there is a possibility of interference if you have same frequency. If you choose different frequencies, you can manage not to have the interference. বুঝছো?
স্যার বাট মানে স্যার আমাদের তো উইল স্টিল হ্যাভ আ কনস্ট্যান্ট ফেজ ডিফারেন্স, তো সেক্ষেত্রে একটু হলেও ইন্টারফারেন্স হওয়ার একটা ইয়ে থাকে না? লাইক আর দোজ মানে মেটিকুলাসলি ক্যালকুলেটেড যাতে হচ্ছে করে কোনো একটা
There is definitely some magic that the people do who do these stuffs, but I totally get your point. I'm sure that theoretically there is a possibility, but I believe that technologically they are overcome. I don't know how, but multiplexing is a very common thing for optical fibers that I know for a fact. Which you will say.
Yes sir.
You might want to look into it for more details, but and you should be able to find it pretty easily. আচ্ছা, এখানে একটা দরকার জিনিস আছে, সেটা একটু খেয়াল করো। সেটা ট্রান্সমিটিং ডিস্টেন্সিয়েশন টি ডিরেক্টস আ ক্যারিয়ার ওয়েভ অফ ফ্রিকোয়েন্সি এফ আপ টুয়ার্ডস দ্য স্যাটেলাইট। দ্য স্যাটেলাইট রিসিভস দিস সিগন্যাল, অ্যাম্প্লিফাইজ ইট অ্যান্ড চেঞ্জেস দ্য ক্যারিয়ার ফ্রিকোয়েন্সি টু আ পাওয়ার লোয়ার ভ্যালু এফ ডান বিফোর ডিরেক্টিং ইট টুয়ার্ডস দ্য রিসিভার আর ব্যাক টু আর্থ। সো এখান থেকে একটা সিগন্যাল যাচ্ছে, এখান থেকে একটা সিগন্যাল আসছে। সো উই বেসিক্যালি ওয়ান্ট সাম ডেটা টু বি ট্রান্সমিটেড ফ্রম দিস লোকেশন টু দিস লোকেশন, and this satellite is helping us to make this enable over the curvature of the earth. So we're talking about like thousands of miles or kilometers of distance. This, and then it says that typically the uplink would have a frequency f of 6 GHz and the downlink would have a frequency f down of 4 GHz. The 6-4 GHz band alternatives are the 14-11 GHz and the 30-20 GHz band. The two carrier frequencies are different to prevent the satellite's high power transmitted signal swamping its reception of the very low power signal that it receives. There is no interference of the actual information being carried by the waves because this is sorted out as modulation of the carrier waves. Achha. Sorry, sorted out. This is stored as the modulation of the carrier waves. My bad. Achha. এই জিনিসটা বলে, এই জিনিসটা তোমাদের কোশ্চেন হয় যে what does it mean by the swamping? This word is a keyword. That what does this swamping means? One of the behavior of electromagnetic wave is that how can I put this? I'm at a loss of words. আচ্ছা, সোয়াম্পিং এই জিনিসটা আমি নেক্সট ক্লাসে বুঝাবো। এটা আমার আগে ইয়াগুলো একটা দেখা লাগবে। মানে আই আন্ডারস্ট্যান্ড হোয়াট দিস ইজ, বাট এটা ওয়ার্ড এখন বানাতে ইচ্ছা করতেছে না। I would like to discuss this set of maths over here. That how can we calculate the attenuation and stuffs. Acha, this is something that I like because I think I am good at explaining this. I'll take this figure. আচ্ছা, দরকার নাই actually. All right, let's have a look. Attenuation is a very important factor. For successful communication, it is important that the receiver understands what the sender wanted the receiver to understand. What I mean is that, let's say, if I am yelling out, "You are stupid," from the end of a lake to a person on the other end, and that person hears out, "You are beautiful," then this is communication, but not successful communication. Successful communication is possible when the exit information that the sender wants to send is received by the person. There are multiple factors that affect successful communication. একটা হচ্ছে how noisy is the communication channel, and also exactly how noisy is the environment around the receiver. So let me show you what this means. Let's say this is a communication channel. এই communication channel input এ আমি power in, এই পাওয়ারের একটা signal send করতেছি. So we're going to send a signal of this much power within this communication channel, and after passing through this communication channel, this communication, I'm trying to show this apparent rectangle as a communication channel. This can be a wire pair, can be a coaxial cable, can be radio link, microwave link, or optical fiber. This is a communication channel. Let's say it is coming out over here as P out. This is the output power. Obviously, output power will be smaller than the input power. The receiver will be receiving this power, output power, and should be able to decipher or understand what this information is. To be able to understand this information at the receiver end, this received power should be somewhat bigger than the noise of the environment. Every environment have some inherent noise that obstructs the receiving of this information. One simple example that I usually give by is that let's say এটা হচ্ছে আমার ডি ব্লক মাঠ, ঠিক আছে, এদিকে হচ্ছে একটা রাস্তা, এদিকে হচ্ছে একটা রাস্তা। আর মনে করো আমি এখানে দাঁড়ায় এখানে এই পাশে একটা স্টুডেন্টকে একটা ইনফরমেশন বলার চেষ্টা করতেছি। Let's say if you are trying to communicate at around, let's say, 6 a.m. in the morning, where the playground is basically empty, we could talk at a pretty low volume and still be able to communicate with each other very easily. But if it is 4 p.m., where the field is filled up with, let's say, 100 plus kids playing around, doing the same communication will be very difficult, because now the channel has become more attenuating, which means as I'm speaking, sorry, the energy of my voice is decreasing a lot, so I'm losing a lot of power. So if I want to make successful communication, I just have to yell out louder or use microphones or something like that. And one thing is also important. Let's say the other example is that, let's say I'm talking from here, let's say at 6 a.m. once again, and here is my student, here is one of my students who is trying to communicate with me, and suddenly one of their friend comes by and they start to talk to them, or multiple of their friends trying to talk to them, and I'm also trying to talk to them. So this is actually a local noise which can interfere with their capability to decipher what I'm trying to say. These are the key two factors which plays an important role in the process of this calculation maths. So the first thing that we're going to see is that what is attenuation? Attenuation is measured or calculated in logarithmic scale, because the amount of change that happens is very large in terms of power, power degradation, or power lower, power that is the value of the power of the signal that gets lowered over the distance. So attenuation of a signal is given by this: attenuation equals to log P in by P out. Now, this is basically telling us that how much the power has become weak. This attenuation in this case is basically meaning that the signal is becoming lowered. If you only get this much, this will be given in bell. If you want to get this whole information in decibel, you simply place a 10 over here, 10 log P in by P out into decibel. there are multiple different ways to remember that which one goes up and which one goes down. This is basically what the students confuse up. Here's the deal. You do not want any of these answers to become negative. Attenuation or signal to noise ratio, all of these things are always a positive value. You can only get a positive number for this answer if this ratio is over here is bigger than 1. Because if you have a smaller number on the top and lower number at the bottom, you'd get a negative logarithm. So if you want this whole thing to be positive, you need the numerator to be larger. That's basically it. So you do that and you do that 10 over here, you get the attenuation part. And then there is another information over here which is important for the communication channel. If the length of the communication channel is, let's say, L, and then we can say that the attenuation per unit length of the communication channel, that can be given by 1 by L multiplied by the whole thing, 10 log P in by P out. Then it would be decibel per meter or per kilometer, whatever that L unit is. That's one thing. The other thing that is important is that এটা হচ্ছে একটা রেশিও, আমাদের এই পার্টটা দিয়ে আমাদের এক্সেট ম্যাচ করা যায়। আরেকটা ইম্পর্টেন্ট পার্ট হচ্ছে যে to be the other important part is that to be able to detect successfully the output signal by the receiver, this signal has to be somewhat stronger than the prevalent noise of the environment, which means this has to be somewhat more powerful over the noise. If the noise is, let's say, whispering, then this coming in voice should be talking. If the noise is talking, then this coming in should be yelling, and so on and so forth. So this incoming information should be somewhat stronger in terms of power quantity compared to the noise value. So what that means is that there is another value, that another information that we work with is that signal to noise ratio, that is given by log P out. P out basically means the P signal divided by P noise, because you have to understand in this case the noise has to be the weak one and the output signal has to be the stronger one for successful combination to work. This would be in bell. If you place a 10 over here, this becomes decibel. So this is the other equation that we have. এই দুটো ইকুয়েশন আমাদের এখানে দেওয়া আছে, or you can write them down. এই যে এখানে একটা আছে attenuation per unit length এর ফর্মুলা দেওয়া আছে, আর signal to noise ratio এখানে দেওয়া নাই। signal to noise ratio এখানে দেওয়া নাই কেন? আচ্ছা, signal to noise ratio ইকুয়েশনটা এখানে দেওয়া নাই, বাট signal to noise ratio ইকুয়েশন আমাদের দেখাইলাম, এটা আলটিমেটলি আমাদের এই যে এখানে দেওয়া আছে, যে এখানে দেওয়া আছে। But that's basically how the equation works out. So এই দুটো ইকুয়েশন তো আমাদের গাড়িখানি ম্যাচ করতে হয়। টু বি অনেস্ট, আমাদের ফুল কমিউনিকেশন চ্যাপ্টারের ওয়ার্কশিট যখন করবা, অ্যাপার্ট ফ্রম গ্রাফ কনভার্সন, আমাদের এই ডেসিবেল রিলেটেড কমিউনিকেশন আছে অনেকগুলো, ক্যালকুলেশন আছে অনেকগুলো। আমি কিছু এক্সাম্পল দেখাই। কোথায় বা কার্সর কই? মাস্টারম্যান, তোমাদের পরীক্ষা হয়েছে? স্কুলে?
স্যার 12 তারিখ থেকে স্টার্ট হবে।
ওকে। You have a look over here. Let's say a transmitter on out processes signal of power 2.4 kilowatt. The signal when received by a satellite is attenuated by 195 decibels. Calculate the signal power received by the satellite. So which means they are basically asking you to find out the output power. So you are sending the signal from the earth. This is the input power. The communication channel in this case is the microwave link or the radio link, whatever that is. And on the receiving end, তোমার power কতটুকু আসবে। So আমি যদি এই ম্যাথটা করার চেষ্টা করি, will try. Makes sense. (195) equals to 10 log P in by P out. 19.5 equals to log P in হচ্ছে 2.4. লাস্টেরটা দিতে বলছো, আনসার ওয়াটে দিতে বলছো, তো আমি 2.4 × 10⁻³ ইউজ করলাম, কিলোটাকে ভেঙে দিছি। এভাবে পি আউট, এখান থেকে এখন পি আউটটাকে সাবজেক্ট করা লাগবে। কেমনে করবা? এটা আসবে হচ্ছে 2.4 3 divided by এরকম না? এরকম আসছে কারো? আচ্ছা দাঁড়াও, মার্সিন দেখি, মার্সিন দেখলে ভালো বুঝে যাবে। হ্যাঁ ঠিক আছে, 7.6 × 10⁻17 watt. So that's one way to do the calculation. There are এটা হচ্ছে similar একটা question, attenuation per unit length বের করতে বলছে। So in this case you find out the attenuation, then divide it by the whole length, then you get the decibel per kilometer unit attenuation per unit length. What is really interesting, এই টাইপের কোশ্চেন গুলোর মধ্যে এখানে এই কোশ্চেনটা অনেক ইন্টারেস্টিং। The idea of this question, আমি এটা আজকে করাবো না, জাস্ট কোশ্চেনটা বলে শেষ করতেছি ক্লাস। It is that to achieve successful communication over a long distance, we have to place repeater station every 6 kilometer apart. So finally বাই করতে হবে হচ্ছে যে মোট কতগুলো repeater station লাগবে। So we're gonna see this math in the next class inshallah, and then we'll pick it up from there. প্রবন্ধ আমি লেকচার টু আপলোড করে দিচ্ছি, যারা ক্লাস দেখছো, if you have any question you can ask me in the next class as well, no problem. If you have any question from the earlier classes you can also ask me. Thank you very much. Good night.